Hello, chemistry students. Today, we're going to be introducing a new unit. It's going to be our unit on reduction and oxidation, which also goes by another name. It goes by the name redox. So whenever we talk about redox reactions, this is exactly what we're referring to. So in this unit, and mainly in this lesson, you're going to have to remember one thing, that Leo says grr. And maybe that doesn't make sense right now, but it's a good tip and trick to remember towards the end of the lesson when we're doing our work. So oxidation and reduction reactions. During some chemical reactions, certain elements may gain or lose electrons as they react to form new compounds, which we've seen all throughout the chemistry year. Oxidation and reduction reaction is when electrons are transferred from one element to another. So there has to be an exchange of electrons between two elements for this to occur. So in oxidation, we are seeing a loss of electrons. And in reduction, we're seeing a gain of electrons. So a quick introduction is that oxidation originally meant combining substance with oxygen, as in the rusting of metals. Reduction was the opposite. It meant the loss of oxygen. But as time went on, they developed more scientific definitions for these terms. And here we see a good example of oxidation. We see a nice metal rusting away, and this is what we thought was happening, is that it was simply just oxidizing. So corrosion is something that we brought up in the very beginning of class, way back in September. And in our first unit, we introduced corrosion as a chemical reaction. And corrosion is damage done to metal, and it is costly to prevent and also costly to repair. Iron, which is a common construction metal, is often used in forming steel alloys. This corrodes by being oxidized to ions of iron by oxygen. So you might be walking by a construction yard, and after a really strong rain, some of that metal construction fencing that's up starts to look a little brown or even tarnished. Now that is oxidation beginning. It's when oxygen is starting to attach itself to the iron atoms. This corrosion is even faster in the presence of salts and acids. And that's because these materials make electrically conductive solutions that make electron transfer easier. This is why the Statue of Liberty changed color. It happened so quickly because the salty bay that surrounds the statue. And the Statue of Liberty wasn't originally this green corrosive color. Originally, it was bright and very, very lustrous. And it was this deep bronze color. But over a very short amount of time, it started to corrode. And that's because of the water that surrounds it. And that water is what? Salt water, which really increased the reaction of this corrosion. So corrosion continued. Luckily, not all metals corrode easily. Gold and platinum are called noble metals because they are resistant to losing their electrons by corrosion. Other metals may lose their electrons easily, but are protected from this corrosion by the oxide coating on their surface, such as aluminum. And this is why you see aluminum outside used for exterior structures a lot, is because if we oxidize the outside of aluminum, it's perfect. It doesn't corrode. Now, for the jewelry you see up here, something pretty cool is happening. We have other metals such as tin, iron, and nickel underneath a gold layer. And the reason why we don't just have material made from pure gold is that gold is an exceptionally soft metal. And what happens is that metal can be easily imprinted on or damaged. So instead of having jewelry that's pure gold, which would be really soft and might damage easily, we dip our jewelry, which is usually tin, nickel, and iron, in a gold bath to cover it in a gilded form. Now, this actually helps to protect the underlying metals from oxidizing because they have a full coating of gold around them. So, electron transfer and oxidation numbers. This is when we get into the meat of the subject. In order to determine whether or not an equation represents a redox reaction, you must be able to assign oxidation numbers to all the atoms involved, just like what we were doing when we were creating compounds with different elemental charges to them. So if an atom's oxidation number changes from one side of the reaction to the other, then the reaction is a redox reaction. Oxidation numbers can be found in the periodic table of elements, and we've been using them so far this year. They are the numbers right here, which previously we were referring to as charges. However, now in our course, these numbers, we're going to be referring to them as oxidation numbers. As you can see, they're called selected oxidation states. So, which is oxidized and which is being reduced? A substance that is being oxidized loses electrons, which means it's an increase in its oxidation number, or it's becoming more positive. A substance that is gaining electrons, which means its oxidation number does what? It decreases. And the reason for this is because it's gaining electrons. It's gaining negative charges. This is why it's called reduction. So, loss of electrons, oxidation, gaining of electrons, reduction. And you can see the charges next to each one of these. This has lost an electron, it's a positive charge. This has gained an electron, it's now a negative charge. So oxidation, an atom loses one or more electrons. Reduction, an atom gains one or more electrons. This is where we come into our topic of Leo says grr. Losing electrons is oxidation, gaining electrons is reduction. Here we have magnesium being oxidized in the reaction above. We have 2 moles of magnesium and 1 mole of oxygen, which is a diatomic. And we end up with 2 moles of magnesium oxide. So when magnesium is being oxidized, we have magnesium starting off and it does not have an oxidation number associated with it. And then it has a +2 up here because we're having it lose those 2 electrons. Leo losing electrons is oxidation. And here we have oxygen in this reaction. It's being reduced. So it's gaining electrons, reduction. Oxygen with a neutral charge or a 0 oxidation number now is gaining a -2. So remember, Leo says grr. So if we're reviewing assigning oxidation numbers to different elements, we're going to have to remember a couple things. An oxidation number is a positive or a negative number assigned to an atom to indicate its degree of oxidation or reduction. The rules for assigning these different numbers are as follows. There's 3 different rules. The sum of the oxidation numbers in a compound must be 0. So in the elements that we've been using to form this compound, NaCl, we've been using them throughout most of the year. We know that sodium is going to have a +1 charge and chlorine is going to have a -1 charge. When they come together, their net oxidation number is going to be 0. All uncombined elements have an oxidation number of 0. Mm. So, neon, which is a noble gas, has no oxidation number. Zinc and silver, they don't have oxidation numbers as metals. And oxygen is diatomic, doesn't have an oxidation number associated with it, and neither does nitrogen. Now, hydrogen is a special case. Because hydrogen is all by itself over with the nonmetals, or sorry, over in group 1 with the metals, hydrogen is +1 when it is with nonmetals, because think of the nonmetals on the right-hand side of the periodic table. They all have negative charges. So to counterbalance this, hydrogen keeps its +1 charge. And when it's combined with other metals, which are usually positively charged, hydrogen will have a -1 charge. And I keep saying charge, but what's the word I should be using here? I should be using, that's right, oxidation number. So reviewing assigning oxidation numbers. Here we have the transition metals from group 3 to group 12. Now transition metals have multiple possible oxidation numbers. To determine their number, you have to do it last. And you should be determining all of the other elements in the compound. You should be determining their oxidation number first. Now, the sum of the oxidation numbers in polyatomic ions must equal the charge of the ion. So, really quick, take out your chart for polyatomic ions in Table E. So, the sum of the oxidation numbers in the formula of a polyatomic ion is equal to its ionic charge. And you can see the ionic charge is there on the side. So, the oxidation numbers in the formula, they're equal to the ionic charges. So you can consider all of these charges to be their oxidation numbers as a whole. So let's do a brief example of finding an oxidation number. What are the oxidation numbers of all the atoms in sodium chloride? Let's break it down. The overall compound must have a charge or a combined oxidation state of 0. Sodium is +1, and therefore chlorine must be -1 to have a combined oxidation state of 0. What are the oxidation numbers of all the atoms in hydroxide ions? Now, take a moment and look at this. What's different about this to this? Sodium chloride and hydroxide. Hydroxide is bonded, and it's hydrogen bonded with oxygen. And remember, oxygen is a nonmetal. So what's the rule we have to use for hydrogen when it bonds with a nonmetal? Is it going to have an oxidation number that's +1 or -1? So oxygen, it has a -2 oxidation state on the periodic table, and therefore hydrogen has to be its positive oxidation state. And we get OH with -1. And it's okay that we have the -1 up there because we determined that hydroxide ions are going to have that charge. So in the end, when we have oxidation states of for oxygen is -2, hydrogen is going to be +1, and the net oxidation state or the combined oxidation state of the compound will be -1. So on your structured notes, you're going to find various different learning checks to practice our assigned oxidation number questions. So we want you to go through these and make sure to fill them out on your structured notes because this is how we're going to check your understanding. So please take a moment to do these. I'll read them to you. What are the oxidation numbers of the atoms CaCl2? What are the oxidation numbers of the atoms in FeCl3? Now notice these first two, there is no little attached charge or oxidation state. Instead, we have a 0. So make sure that you're planning these out to be 0. What is the oxidation number of chromium in CrO4? What are the oxidation numbers of all the atoms in H2SO4? Good luck, and please remember, students, we're always available via Remind, or you can come onto Google Classroom if you ever need assistance. Hope you have a good day.